All right, A4. So this now is, oh, this is now a heteronuclear diatomic, right? So now we're talking about boron and nitrogen. And so again, right, we do the same thing that we would normally do where we draw the two atomic orbitals first on both sides, right? So I'm going to have boron over here, and then over here, I'm going to have nitrogen. And so one easy thing that you can do if you aren't given the energies is you just simply think about the electronegativities of the atoms involved, right? So if you know look at the periodic table, nitrogen is going to be more electronegative compared to boron. So if it's more electronegative, then that means that when electrons go into it, they're going into lower energy orbitals, right? So we would then expect the atomic orbitals to be lower in energy for nitrogen, right? The 2s and the 2p will be lower in energy on nitrogen compared to boron, right? Where again, we would still be looking at the 2s and 2p in those cases. And so, right, so if we go and use that logic, right, I'll just simply draw my 2s right here, and then I'll draw my 2p right here. And so then the 2s for boron should be higher than the 2s for nitrogen. So I'm going to say that's about right here, right? And then I would expect the 2p on the boron to be higher in energy than the 2p on the nitrogen, right? So that would be somewhere up here in those cases, right? So we have that. So now going through, boron, right, has 3 electrons. So we go 1, 2, 3. Nitrogen has 5 electrons. So we have 1, 2, 3, 4, 5, right? So now both of these are done, right, for the atomic orbital energy, right? And so now the next thing is then drawing the MO diagram for BN, right, for boron nitride. So now follow the exact same approach that we had done in the past, right, where we have s orbitals interacting with each other to form sigma bonding and sigma anti-bonding orbitals, right? And so now the sigma bonding orbital should be lower in energy than the 2s on the nitrogen, right? And then we should have a sigma anti-bonding orbital that should be higher in energy than the boron 2s orbital, right? So that should be somewhere right here, right? So that's done. Now, the next thing is, right, if we think about that trend that I'd mentioned when I was talking about problem A3, right, talking about O2, is that there is a split in terms of what the ordering is when you go from nitrogen to oxygen, right? In the case of oxygen, what you have is that the ordering is, you know, sigma, sigma star, sigma, you know, the 2 pi's, the 2 pi stars, and then sigma star at the top. In the case of nitrogen and below, right, in that second row, what you have is sigma, sigma star, the 2 pi's, sigma, the 2 pi stars, and then sigma star, right? And so that has to do with sp orbital mixing. That relates back to, and I don't think that's something that you guys are gonna, you probably didn't go over, and I don't remember off the top of my head how much the textbook really goes into it, but basically, it, you know, just the same way as if you have, you know, for an MO to form between, you know, two 2p's, they have to be close enough in energy and stuff. If you have the s orbitals on one and the p orbitals on a different one, even though the other one has p orbitals, right, those can still form bonding combinations, and so you make these, you know, very complicated molecular orbitals that actually involve a variety of different atoms on the different species, on the different atoms, right, that change up that ordering in those cases. And so in terms of how to approach the heteronuclears, if you have a if one of the atoms that's involved, right, is one of the ones before nitrogen, that's going to stay, right? So in this case, both of them are, so that's definitely going to stay. But if you had something like NO, right, so nitric oxide, right, that's going to then have the ordering that follows the nitrogen, right? If you had something, you know, like NF, right, that would follow the ordering for nitrogen in those cases, because again, the two atoms that are on, or sorry, the 2s and the 2p then on that nitrogen, right, can still interact and do, you know, the weird mixing stuff with the 2p orbital on, you know, the fluorine or the oxygen in those cases. But yeah, so I mean, so then when we draw it here, right, we're gonna have then our pi orbital here, right, and then we're gonna have our sigma orbital right here, bonding orbital, right, and then up here, you know, above the 2p of the boron, we're gonna have the 2 pi stars, and then, you know, into the text right here, we'll have our sigma star there, right, I kind of ran out of space, right, so these guys are all here in these cases, right? And so that right there is the backbone of drawing the MO for BN. So if we plug in the number of electrons we have, right? So we have 3 from the boron, 5 from the nitrogen, right? The total number of electrons that we would expect for BN is going to be 8. So if we plug those in, right, what we have is 1, 2, 3, 4, 5, 6, 7, 8, right? So what we would expect based off of, this MO diagram right here is to have, this ordering right here, where we have the, excuse me, the, 4 electrons in the filling up the 2 pi orbitals in that case, and the sigma bonding orbital being empty for BN. And so then the next question is in the series, on the basis of your MO diagram, would you expect the boron nitride cation to have a more or less stable BN interaction? What is the justification for our answer, right? So if we're going to be forming the cation, that means we're going to have 1 less electron. So if we go back and we calculate the bond order, right, of BN in this case, right, what we have is 1, 2, 3, 4, 5, 6 electrons in the bonding orbitals. Come on. Technical difficulties. At least this time it's not the pen. It's just not letting me switch things right now, which is fine. Whatever. All right, so I can just draw it all right here, right? So the bond order for BN is 1, 2, 3, 4, 5, 6 bonding orbital electrons, and then 1, 2 in the anti-bonding, so -2. So we take that, divide that by 2, right? What we get then is 4/2, so that comes out to 2, right? So we would expect a bond order of 2 between BN. Now, if we were to go to BN plus, right? So if we were to do that now, that would change up, what the orbital filling is in that case, right? So we're going to lose 1 electron. So if we lose 1 electron, so we lose 1 electron, right? We're going to lose 1 out of the pi bonding orbital. So now that's going to then be 5 minus 2/2, right? So 5 minus 2/2 comes out to 1.5, right? So now all of a sudden we only have a bond order of 1.5, right? So the lower the bond order, the less stable it is. It's still going to be stable, right? It's still going to be bonded and everything. It's just not going to be as strong. It's not going to be as stable as it would be, if it was on its own. So, that's how you end up with a bond order of 1.5 in that case right there. The next question, right, was then if you add an electron into it, right? So if you have BO, if you do the bond order then of, BN minus, right, you're putting 1 more electron in. So if we put 1 more electron in, that would fill into right here, right? And so then now we have, instead of, 6 bonding electrons, right, we would have 7. So that now would be 7 minus 2 divided by 2. So what we get now is a bond order of 2.5, right? So with a bond order of 2.5, right, that's going to be a stronger bond, right? Because now the bond order is higher. And so with a higher, bond order, we would expect that to be more stable. We would expect that to be a lot stronger. So it's going to try to change pages with my keyboard right here. All right. So, right. And so those are the justifications that you would really need to have in those cases. Is you would just, go through, calculate the bond orders, right, and use that as your reasoning.